Description of the project. In this project, RTL design of processor named FB-CPU was carried out with Verilog language. Various code snippets are written in the machine language on the designed processor. The FB-CPU RTL design is in von Neumann architecture. At the end of the project, it was observed how the RAM, control unit, and decryptors in the simple processor can work together to execute code snippets in machine language. Von Neumann architecture. The CPU has four main units: registers, memory, processing unit, control unit. The task of the units used in von Neumann architecture is: the memory holds the operation commands and variables, the processor unit performs arithmetic and logical operations, the control unit is necessary for the decoding of commands, and registers are storage areas used for various tasks. Hiders. There are four repositories defined in the file. State, the state machine keeps information about the state it is in. PC, information on which address in RAM the command is running is kept. IR, the currently running instructions itself is kept. ACC, temporary storage area. The memory signals connected to input and output ports in the design are given below. MAR 6-bit. The register is connected to address input of RAM. Since RAM has 2/6 locations, MAR is 6 bits. The register is inside of the RAM. MDRIN 10-bit. Memory data register is a register used when data is written to RAM. Since one location of RAM is 10 bits, the register is 10 bits. The register is inside of the RAM. RAMWR 1 bit. It is activated when data will be written on RAM. If it's not 1, no data is written on RAM. The register is inside of the RAM. MDROut 10-bit. Memory data register is the register used when data is read from RAM. Since one location of RAM is 10 bits, the register is 10 bits. The register is inside of the RAM. As you see, the operations supported by the FB CPU are given in Table 1. The processor supports 9 commands. Figure 3 shows the separation of bits of the 10-bit command of the FB CPU for operation and address. The software used. The design was coded in the form of a state of machine. Case is looking at the situation and is constantly progressing according to structures within the situation. The state diagram of FBE CPU, expressed as a state diagram, is shown in Figure 5. The tasks that the processor needs to do step by step are shown decoupled. The reason we use a status store is that the store, which indicates when all the working mechanism in the system will work, works according to these steps. Case 0. In case 0, our storage named program counter set the value of the storage in which we keep whichever command we are going to run in memory. Since we did not perform a write operation, we switched our write signal RAMWR to 0 and increased the state by 1, jumping to state 1 after one cycle. So here we have giving the value of the PC to MIR so that it is 0 from RAM. We asked for the contents of the address. When we changed the status, RAM gave us 0 from its own data output from MDROut. It will return the contents of the address. Case 1. When we switch to state 1, the incoming instruction information from memory data out is written to instruction register so that it is not forgotten. Because we will return to state 0 again after transactions, the 0 we read earlier when the state was at 0, not the address but 1. We need to read the addresses. We have increased the PC by 1 for this. After performing this operation, we also increase our status by 1 to perform the new operation and move to state 2. Case 2. The storage we assigned to the IR in the previous step is 6 out of 9. We are looking to see if the bit is smaller than 6. The reason we are looking is that all transactions less than 6 need to read an address from RAM. We do not need to know the content in a single STO. Since we need to read the content in the first 6 operations, the processor is designed with the logic of reading the contents of all of them and taking them to state 3 and finishing the remaining task in state 3. If the bits from 9 to 6 are less than 6, the address is stored in the first 6 bits of the IR, because we will need the address and the contents of the address. We wrote this on RAM's MAR, so we want an address from RAM again, but this time the address we want is the address written next to the comment there. After these procedures, we took the situation to say 3. So if it is one of the first 6 process, we ask RAM for this information because we need to reread the address content. So our status change depends on the first 6 bits. If the first 4 bits from the left in our machine code are smaller than 6, we have bypassed the situation to 3. If the incoming value is 6, we equalize the PC value to the number corresponding to the value of IR from 5 to 0. We are also returning this situation to 0 again. So actually the JMP command has arrived. We have written the new value of the PC. When we take the status back to 0, the PC value will not be updated because the process that we will read from RAM will now be the location of the code that we will pull from RAM from the updated location, and we will have performed the JMP operation. 7. The feature of the command is conditional JMP operation. If the ACC value is 0, we assign the PC value, the value of the first 6 bits of IR, and go to status 0. If not, we do not change the PC value, we send the status to 0 without any action. If the command 8 has arrived, the NOP command, that is, no action is taken, we only return the situation directly to 0. If operation code 9 comes, HLT is performed, so the code stops. We are jumping to situation 4 to make it stop. Case 3. After reading the first 6 operations from RAM, we use it to perform operations. When we switch to state 3, we take our future state directly to 0. That is, we go direct to state 0 one cycle after the operation we've performed. In the image on the side, we have synchronized RAMWR and MAR to 0, but we can update their values in the operations on the lower side. If IR is equal to 0 from 9 to 6, it means that we are doing LOD operation. LOD takes the contents of that address and throws it into ACC. We actually ask for the content of that state by giving it to MR in state 2 and comes to us from MDR out one cycle later. We are throwing this at the ACC. When the operation code is 1, we assign the value inside the ACC to the value inside the memory with the STO command. To do this operation, we gave MAR address of the place we told IR 5 to 0. We made RAMWR1 at the same time. We are loading the data content of RAM. We also gave the ACC value to your MDRIN. Here we gave the ACC content from memory's data port. We made written 1. And at the same time we gave the address from the STO process. The entire STO is a 10-bit number and we kept it in the IR storage. When we gave 0 out of 5 of the IR storage, we gave that 6-bit address to MAR. When the operation code is 2, when the add operation is performed. We had done the process of reading the address content a cycle ago. The address we read came from the memory data read register out. We collected it with ACC and wrote ACC again. When the operation code is 3 sub, that is, when the extraction job comes, we have adapted the steps in ADD process to the extraction process. In other words, we extracted the value from the memory data read register out with ACC and wrote it back to ACC. When the operation code is 4, the multiplication operation is performed with the MUL command. The value from the MDR out is multiplied by ACC and overwritten by ACC again. When the operation code is 5, a division operation is requested with div command, but since it involves a process complexity above our level, we will send the status to 0 without taking any action when the operation code is 5. Case 4. In case 4, nothing is just checked, nothing is done, it just turns on. Where is also no exit command. When the HLT operation arrives, it will not be possible for the processor to exit from here if the power is not turned off, and restart. For the FB CPU, the number with a hexadecimal equivalent of 5 to 50 addresses in memory is loaded in the ACC storage with the LOD command. 50, which is located inside our ACC storage with the ADD command, value of the address. 51, the expression with hexadecimal equivalent A in the address is collected. With the STO command, the value of ACC store will be registered to the addresses. The test is also stopped with the HLT command. Test case 2. For the FP CPU, the number with a hexadecimal equivalent of 5 to 50 addresses is in the memory is loaded into ACC storage with the LOD command. 50, which is located inside our ACC storage with the MUL command, the value of the address is multiplied by the expression with hexadecimal equivalent A at address 51. With the STO command, the ACC store's value will be registered to the address. The test was also stopped by the HLT command. Test case 3. The operation that we are asked to do for the FB CPU is multiplication, but we need to do it with loops, not with the MUL command. 51 in memory, the value in the address is registered to ACC with LOD command with the sub command. 49 in subtracted from the value in ACC and saved back into ACC storage. With the JMZ command, the result of the operation we performed in the previous step is checked to see if it is equal to 0 or not. If it is equal to 0, exit the loop and enter 10. It goes to performed transaction at the address. So 48 loads the value of the temp at the address into ACC storage. The value in ACC with STO is 52. It registered it to the address and then finishes the code with HLT. In this way, with loops, the result is saved to memory without using the MUL command. But if JMZ is not equal to 0, ACC 49 continues to rotate until it becomes 0. After the checkup, 48 loads the temp value to the address with LOD. 50 adds the value in the address with ADD OCT on top of ACC. 48, it goes to the address and registers the value of the ACC in the STO temp. 49, assign the value in the address to the ACC and enters 46. Collect with the value at the address and 49. He registers again the address, 0 again with the GMP command. It returns to the line that is to the beginning of the cycle. Results. The operations supported by the developed processor are taken from the FB CPU ISA table. When expressing the FB processor in the Verilog language, the ALU, that is the arithmetic processing unit, is the part where arithmetic operations are performed. There are 3 arithmetic operations in the FB CPU. These are addition, subtraction, and multiplication. Operations are performed according to the incoming operation code and written to ACC storage. Test software 1, test software 2, and test software 3 were tested one by one and examined via simulation on Vivado. Our algorithmic thinking ability has improved and our mastery of the Verilog language has increased.